Good day, and welcome to this presentation of Chemistry and STEM. In this presentation, we'll look at different ways to solve real-world problems in the context of STEM education. So let me quickly review what we're going to cover in today's presentation. First, I'd like to share with you some of my personal experiences from when I was working in industry, and I'll use these experiences as a foundation for designing chemistry labs that would place scientific theory into an appropriate real-world context. Next, I'd like to talk a little bit about what STEM is, as there's always a lot of confusion surrounding the true nature of STEM education. Next, I'd like to give you some real-world examples of chemistry in use that you can use to design authentic chemistry labs with. These examples will include how to conduct a water analysis using the same methods as health and safety lab technicians use, the use of chemistry in photography, and this is a great way to create cross-curricular lessons that will create rigorous academic learning outcomes while also including the arts. And finally, how we can recover precious metals such as gold from e-wastes. And this chemistry lab would also lay the foundation for some excellent philosophical debates that range from the environment, social, and economic impacts of our actions. So let's start with big idea number one, drawing on experience. One of the best ways to design and build authentic projects and curricula is to draw on lessons that you have learned from either personal or professional experiences. Therefore, I'd like to share with you some examples of how my experiences from working in industry have provided me with some invaluable insights into how chemistry can be applied to everyday problems. And I'm going to show you how we can use that knowledge to create authentic learning opportunities that uphold the ideology of STEM education. Now, I started my first company in 2002, and by 2005 my company was officially operating with a federal tax ID. Now, my company was a small private consultancy that took on numerous projects over the years. Then, in 2010, my work in 3D imaging technologies took me to Korea, and by 2012, I had patented the world's first 3D reflex microlens imaging technology. Now, if you're interested in this work, you can always review the patents should you like. I have the appropriate references numbers up on the screen. However, unknown to me at the time, my work in 3D imaging would eventually take me into some interesting and unexpected markets. Although I would have never thought it possible, my work in 3D imaging brought me into the realms of cosmetics. Yes, you heard me right. My work in 3D imaging brought me into the world of cosmetics. Although these things seem completely different from one another, the company that I was consulting for at the time had numerous business operations that involved a single supply chain. This supply chain started with importing raw materials, mostly from China, but also from America, Japan, and Germany. Many of the materials that were being imported included compounds such as titanium dioxide, tin oxide, ferric oxide, and those chemicals were then further refined and then resold. But the first thing that we need to do was to do a quality test of the raw materials. If the raw materials did not contain lead, then the raw materials could be used in the production of cosmetics. However, if the lead content exceeded a certain threshold, then the materials would be diverted to industrial applications. These applications included automotive paints and the development of electronics. Therefore, these raw materials might be used to create cosmetics or electronic products. And that's how my work in 3D imaging brought me into the world of cosmetics. Now, this aspect of my work gave me an amazing opportunity to learn something new and that was completely new to me. And I can now use these experiences when designing projects that apply chemistry in an authentic way to solve real-world problems. Now, I can't go through everything that we did, but I want to focus on a few key compounds to illustrate how real-life experiences can be invaluable to developing authentic STEM lessons. However, the most important compounds that we used were titanium dioxide, tin oxide, ferric oxide, and mica. Using these compounds, we created different compositions that were used by a wide variety of cosmetics and industrial applications. Although we had hundreds of combinations, here's a brief list of some of the most important ones. Our Crystal White series included a high sheen pigment that utilized titanium dioxide, and a secondary formulation which used tin oxide to create a pigment that had a slightly warmer color tone. Next, the most popular pigment in our iron metal series used aluminum potassium silicate, which is also known as natural mica. The natural mica was then mixed with ferric oxide to produce a soft, lustrous compound that had a reddish tone to it. Due to the unique nature of this composition, the pigment was used extensively in the production of cosmetic products, such as blush. And finally, our premium series used natural mica in combination with other compounds that we've already discussed. So, as you might have noticed from the previous slide, titanium dioxide was a key component in the creation of many of the most popular product offerings. Now, titanium dioxide has a high reflective index value, and this results in a brilliant white pigment that is often referred to as a perfect white. Some of the applications of titanium dioxide include cosmetics, sunscreens, and even toothpastes. Moreover, most sunscreens that are designed for infants or individuals with sensitive skins are usually designed based on a titanium dioxide formulation due to its high reflective index and UV resilience. The next compound I want to talk about is talc, which is more commonly referred to as baby powder. Talc has a low luster appearance that ranges from translucent to opaque. On its own, talc is greasy to the touch and has a whitish gray color. It is often used in cosmetics and baby powders as it has astringent characteristics, which helps to reduce rashes. However, talc can also be a bit tricky to work with as it's not water soluble. However, it can be dissolved in dilute mineral acids. And finally, I'd also like to talk about secrete, which is also known as natural mica. While there's many different types of natural mica compounds that are available on the market, we used aluminum potassium silicate. Untreated natural mica produces a low luster pigment which does not absorb oils. Therefore, colors may fade if an individual's skin is very oily. It's good for use in lighter colored foundations and can be used in concentrations as high as 100%. When treated with dimicone, which is a non-toxic silicone-based polymer, natural mica will have a higher lustrous value and improved water resistance. However, high reflectance values means that lines will become more noticeable due to higher contrast values. As a result, this formulation is often very unflattering for older individuals. However, this formulation does help to absorb oils, so colors stay truer for longer. When treated with magnesium myostrate, which doesn't absorb oils, the formulation will create a compound that's well suited for dry skin types as well as darker skin foundations. Because of its increased adhesion to skin, improved wear resistance, and its high binding power, this formulation is ideal for decorative cosmetics. However, this composition is unsuitable for individuals with oily skins. Now, without revealing too many trade secrets, we would also apply a silicone coating to many of the products that were destined for use in cosmetics. This silicone coating would add hydrophobic characteristics to the various compounds. This silicone coating would then be applied as a liquid mist as the pigments were being mixed. This process happens slowly to ensure evenness and consistency. Finally, a small amount of heat was applied during the mixing process to evaporate the solvent, which helped to ensure that the mixing process didn't produce any clumps. The whole process would take about 30 minutes per batch and used an alcohol-based solvent. Now, why did I tell you about my unexpected foray into the world of cosmetics? Well, making lipstick in class can be a fun way to get students to learn how to use lab equipment. Moreover, it also applies basic chemistry skills to create real-world products that the students can actually use. But more importantly, it's also a great way to inspire young women to get interested in STEM education. While your students are not going to be able to produce mass-produced cosmetic products using the compounds that I've discussed earlier, specifically as they'll not be able to conduct the necessary quality control requirements to ensure that the final products are safe for human use, it's still possible to simulate the big ideas by creating organic approximations that would accurately simulate a real product. While exact chemistry will not be needed in this example, students would still need to be able to practice using various lab skills, which would make this kind of activity a great point of entry project for middle school students. So let me explain how you could make lipstick quickly and easily with your students. Everything that you need is currently listed or shown here. Now the first thing that you'll want to do is to melt beeswax, shea butter, and some coconut oil in a glass beaker. But make sure you do not use a direct heat source. Therefore, it's best to immerse the beaker in hot water. Hot, not boiling. Next, once melted and mixed, remove the mixture from the heat source and add any desired scent or color additives. Then, once all the ingredients are mixed, pour the mixture into a lip chap container. Be sure not to fill the mold all the way to the top, as the lipstick will expand slightly as it cools. While you can use an inexpensive silicone mold, you may also consider using professional grade stainless steel molds as well, just like what we would use to create pre-production testers in the lab. Either way, with minimal prerequisites, you and your students can apply chemistry in an authentic way to create a real-world product in about 1 hour. And this kind of activity should really help to get some of the young women in your class just a little bit more interested in the sciences. And that brings us to big idea number 2, which is improving our understanding of the true nature of STEM education. So you're probably thinking, what other experiments can I do in my classes that will apply chemistry in a variety of real-world contexts? And this is what STEM is all about. Using science, technology, engineering, and math skills in an authentic way through a variety of real-world lessons. But there's so much confusion around STEM education nowadays, so it's important that we take a moment to develop a common understanding of STEM education. It's widely accepted that STEM stands for science, technology, engineering, and mathematics. It seems that everybody knows what STEM is, but there's still a lot of confusion and uncertainty surrounding STEM and all of its derivatives. So let me delve into this a bit more. Now, I think most people are aware of Bloom's taxonomy, but for those of you who don't, Bloom's taxonomy is a classification of the different levels of thinking or cognition, where knowledge is at the bottom, and as we delve deeper into our understandings, we can start applying what we know and eventually start synthesizing and evaluating the results of our own thought process. And I think that this is an important thing for us to stop and think about. Everybody seems to have knowledge of what STEM is, but very few people understand the true nature of STEM education. And we as educators know there's a big difference between knowledge and understanding. Now, because of the confusion surrounding STEM, there's been numerous criticisms made of the framework over the years. While these criticisms are valid, they only identified a problem without understanding what caused the problem in the first place. And this criticism has resulted in a number of STEM derivatives which have only created more confusion and for educators and administrators alike. So let's look at some of these acronyms. We have STEM, and we also have STEAM, which adds creativity through the arts. But we have STEMS, which recognizes the importance of social science by adding S at the end of the acronym. STEMA, which adds managerial arts and was first proposed by Harvard University. Next, we have eSTEM, which recognizes the importance of developing English literacy development, and this idea of including ESL curriculum into the STEM framework is an important concept for non-English speaking countries, so that students can access a wider range of research materials, which will help them become more innovative. Which leads us to another derivative known as STREAM, which adds reading and research. And finally, we have STEM with a double M, which was created by Dr. Stephen Meyer and Reverend John Gretz, who added the values of Christian missionary to the mandates of STEM education. While slightly religious in nature, this idea does tie in with the recommendations that were made by the World Economic Forum about considering the social aspects of what we do, but it does it from a slightly religious standpoint. However, this idea does align with the Chinese interpretation of STEM, which they refer to as STEM plus 四肢教育, or moral education, which addresses this need for this need from a more secular standpoint. So this definition of STEM education upholds the original ideology that Judith Ramley had for STEM when she introduced the concept back in 2001. Let's take a moment to read through this definition together. STEM education is an interdisciplinary approach to learning where rigorous academic concepts are coupled with real-world lessons as students apply science, technology, engineering, and mathematics in context that make connections between school, community, work, and the global enterprise, enabling the development of STEM literacies and with it the ability to compete in the new economy. Wow, this definition is incredibly verbose. So I'm going to highlight a few key words here. Interdisciplinary approach, rigorous academic concepts, real-world lessons, apply science, technology, engineering, and mathematics in context to compete in the new economy. As we can see by this last statement, STEM is linked to economic goals to help students compete in the new economy. Therefore, we can't really forget about this connection because it's really the main driving force for STEM at the government level. But let's try simplifying this definition before moving on. STEM solves real-world problems using science, technology, engineering, and mathematics. This is the simplest definition that I can make to define STEM education. However, this perception of STEM education, which I've represented by a red box, is incredibly limited. Therefore, we need to add a little bit more depth to our working paradigm. So let's expand on this idea a bit more and add a bit of depth to our understanding of STEM education. So if our aim is to solve real-world problems, then the problems that we explore should be authentic. By extension, the solution to that problem should also be authentic. And finally, the approach should also be cross-curricular in nature. But professionals in the field of STEM are also addressing real-world needs in our society. Therefore, these industry professionals are leading innovation through creative problem solving. Now we have a definition that's much simpler to understand, and it still upholds the ideology of the original definition that we had previously looked at. However, there's still one last point that I should really emphasize. Although students will often learn numerous hands-on skills in a STEM class, the focus of STEM education is not to develop job skills for a general labor market. So, in conclusion, I'd like to share this graphic with you to show you how all these different concepts are interconnected with one another. From the various subjects that STEM is comprised of, the critical industry sectors that STEM is related to, the educational theory that intersects with STEM education, and the various stages of cognitive development in children. As you can see, the core subjects, science and mathematics, act as columns supporting everything, and these core subjects are supplemented by interdisciplinary subject areas. Therefore, STEM acts as a merging point for the core subjects as we apply rigorous academic concepts in real-world lessons that will help students prepare themselves for the new global economy. However, there are so many critical sectors that are represented by STEM. Therefore, after we see the merging of the core subjects, we also see STEM branch out into a wide range of specializations that all fall under the STEM umbrella. These create an hourglass shape as we take multiple subjects, bring them all together, and then branch out again as we go on to specialize in specific fields of study later on in life. And that brings me to Bloom's taxonomy. As you can see, we always start with knowledge, and as we learn the basics, we start to understand abstract concepts. These concepts could include how to solve an equation or how molecular bonds work. And these are important concepts to understand if we're going to start applying these theories in a STEM program. Therefore, the core subjects really need to precede STEM because we cannot apply math and science before first understanding the basics. Then, in STEM, we can start applying what we've learned in an authentic context to solve real-world problems before we can move on and analyze the results. And finally, later in life, industry professionals are required to synthesize seemingly unrelated concepts to solve complex problems in the real world. And of course, they'll need to evaluate the effectiveness of those solutions as well. Next, we can look at where there's going to be the greatest impact for STEM programs of study. Since critical thinking, math, and science are crucial skill sets to STEM education, you'll find that STEM will have the greatest impact when it's taught at the middle and high school levels. And this notion also corresponds well with what we know of Piaget's theory of cognitive development, which indicates that logic and abstraction only starts at age 12 and continues through adulthood. Now that we have some common understanding about STEM education, let's look at some classroom examples to determine if these classroom projects represent the true nature of STEM education, and what we can do to modify our lesson plans to ensure that we are achieving the desired learning outcomes. Let's start with this STEM project. This was a project that was used to promote the school's STEM program. Now, what grade level do you think this project was for? What about now? This project was a grade 12 honors chemistry project where the students were learning about creating water-resistant paints. Now you might be thinking, just as I am right now, this activity does not appear to be appropriate for that 8th grade level, but the school was proud of it because the students had used the school's lab spaces and had also been engaged in a hands-on learning activity. Now here's some more images from that post, and as you can see, these grade 12 students are in a well-equipped chemistry lab creating paints using craft glue and ground up colored chalk. but we're probably asking ourselves, where is the real chemistry? That being said, designing authentic STEM lessons are incredibly difficult, especially if a teacher has never worked in industry before. Now, I should state that this teacher was an amazing teacher, specifically when teaching theoretical concepts. However, they had a limited understanding of how science was used by industry professionals. Now, there's so many different ways that we could have made this project more appropriate for grade 12 students. So here I have some examples of how we could have done this instead. On the left, I have reference to how we could use a chemical compound that would allow for a thermochromatic effect to be explored. This is when the color of something changes because of a reversible chemical reaction due to changes in temperature. Next, on the right, I have an example of how you can create ferric oxide to create a color pigment. And as we've already seen, ferric oxide has numerous applications in the cosmetic and industrial paints. Therefore, we already have a few options that we could use to improve this one project. But let me take this a little bit further. Now that we have some pigments, we can then explore different chemical methods to convert this pigment into a usable paint. First, we could look at how to use different chemical solutions to create a binding agent and chemical solvents. Alternatively, we could look to our past to learn how some of the greatest minds of our time created masterpieces such as the Sixteenth Chapel. At this point in time, paints were made using pigments such as ferric oxide and lapis lazuli, which were ground into fine powders. These pigments were then mixed with egg whites to create a molecularly stable, organic compound that could last for centuries. So with a few simple changes to this project, we could easily redesign it in a way that would make it much more meaningful to the students. Next, I want to talk about fads versus enduring knowledge, or more specifically, looking at developing sustainable curriculums that can withstand the test of time. Here I have a post showing a project that I personally really like, a CO2 dragster. And this one project is one of the best-selling STEM project kits from companies such as Hygienius and Pitsco. But this one product has been sold in the United States for close to 70 years now, well before STEM ever existed. For example, here's the Pitsco Guide to Education from the 1990s, but CO2 racers were popular way before then. In these final examples, you can see some of the kits from the mid-1950s, which were popular activities at the time as they helped kids get interested in aerodynamics and propulsion during the US-Soviet space race. Now, we can see the influence of this idea of rocket-propelled vehicles as a major driving force in our modern society, even to this day. From the development of the fastest land-based vehicle, which was essentially a rocket on wheels, to our modern-day maglev technologies. All these advancements came from the study of propulsion and aerodynamics. Which brings me to my next example. While over-the-counter do-it-yourself kits provide educators with easy, ready-made projects that can be implemented with little or no preparation, these kits tend to offer very little towards achieving the desired learning outcomes of the established curriculums. However, rocketry has so many meaningful and wonderful grade-level extensions for students, specifically in an upper-year science program. For example, here's a balanced chemical equation for a combustion-based reaction that students can use to make a rocket. Now let me explain what's happening. First, we have potassium nitrate, or fertilizer, which is mixed with regular table sugar. Providing this chemical mixture does not encounter a flame, it will remain relatively stable. However, it's capable of creating a powerful reaction that will create a large amount of thrust. This reaction will result in the formation of an inorganic compound, carbon dioxide, and water. Now, as an instructor, I wouldn't give my students the balanced chemical equation. Instead, I would start with a review, and then I would have my students balance this equation on their own before checking their work and moving on. Then, in order to create the most effective rocket fuel, the students would need to determine the molar mass of each compound in order to determine the correct ratio for the entire mixture. With the math completed, the students would then be ready to create their own rocket fuel. Now, as it stands, this project would have them apply chemistry in an authentic way. However, it still wouldn't have the students apply the scientific method, and I have a perfect method to do that. What would happen if you added aluminum to the mix? Would it improve your rocket's performance? And what evidence can you provide to support your claim? In this case, students would need to formulate a hypothesis that we could go on and test. Now, in theory, adding something that's not necessary to balance the chemical reaction is ill-advised. However, adding aluminum to solid rocket fuel is a unique exception to that rule. Let me tell you a little bit more about this phenomenon. In the early 1950s, Keith Rumble and Charles Henderson conducted a series of experiments where they added aluminum to conventional solid rocket fuels. The results of their experiments indicated a dramatic increase in the exit velocity of common combustion gases. This new chemical formulation was so powerful, it was able to produce similar levels of performance to liquid fuels such as kerosene and liquid O2. Therefore, due to the unique nature of their research, the US Navy was able to significantly increase the range of ballistic missiles and orbital rockets. Now, because this was a bit of a trick question, almost every student's hypothesis will be disproven. However, this will give them a great opportunity to conduct some internet research and look for answers. But how would we test such a hypothesis? Using a simple analog force gauge, we can test the amount of thrust produced by each rocket. Or, for a bit more accuracy, we can use a digital force meter to easily record and export precise data from our experiments directly to the computer. Now you can see what a simple setup for testing homemade rocket engines would look like in this photo. And finally, if your school has a metal shop, you may consider manufacturing your own custom-designed rocket engines using a small metal lathe. As you can see from this example, when you develop a fully cross-curricular approach to teaching and learning, which is what should be happening in STEM, your projects will go much deeper into the core curriculum. And this type of in-depth and insightful exploration, that's what's going to make students more competitive in the new global economy. And that brings us to big idea number 3, where I'd like to share some specific examples of how chemistry is used to solve real-world problems, and how we can use these examples to create authentic lessons that apply chemistry in an appropriate real-world context. The first real-world example that I'd like to share with you is related to analyzing water samples. Now, water seems simple enough. However, it's actually a highly complex substance. This is because water acts as a medium for numerous chemical reactions that can occur in tandem with other chemical reactions, as you'll see in just a moment. Now, students are often taught how to use test strips like these, or litmus paper in class. However, commercial water test requires much more accurate and sophisticated approaches to testing a sample. And personally, I don't recall a single time where I used test strips while working in the industry. This is because test strips only measure key metrics, while also lacking precision. The results can easily be skewed, and test strips do not show the relationships or correlation between different metrics. Therefore, all these factors make test strips relatively unreliable. While they're perfectly fine for teaching the basics in a controlled situation, outside of the classroom, test strips have very limited to no real-world value. Therefore, field chemists will often use professional testing reagents or digital meters to collect accurate and precise readings. For instance, experienced environmental engineers will often conduct tests using specialized dissolved oxygen test kits, which use very specific chemical reagents. Alternatively, things like this dissolved oxygen meter may also be used, and many schools already have Pasco or Veneer lab equipment in their school science labs, which students could use to conduct similar tests and experiments for themselves. And these kinds of water tests are critical to the preservation of our hydrological cycles and the management of our freshwater supplies. And to illustrate this idea, here's a photo that I took on my last trip to Yunnan province here in China. One thing that caught my attention during my trip were these devices. They were being used to increase the amount of dissolved oxygen in the lake water, which was reducing the number of toxic algae blooms and helping the aquatic life thrive. As a result, the water quality in these lakes has drastically improved over the years to what you see today: clear, crystal blue lakes. Now, this would be a perfect STEM project for students to undertake: design, build, and test a water oxidation device. However, this project would be more in line with engineering practices than chemical testing applications. For instance, testing dissolved oxygen is relatively simple with a digital meter. However, what makes environmental engineering demanding is the continued testing and follow-up. For instance, the technician or engineer would need to test the oxygen levels for an extended period of time. In this case, the environmental project in Yunnan, it's already been going on for 10 years when I had visited the county. As such, this kind of data collection and analysis isn't practical for high school labs. Therefore, we need to look for something that has a little bit more immediate results. Luckily enough, many schools have access to a great resource that they can use to conduct some real-world water analysis that probably is far more relevant to the students' everyday life. So many private schools that I've visited have their own swimming pool, or at the very least, they have access to tap water that they could test. Now, if your school has access to a swimming pool, the students can test the water, identify any potential problems, and then determine what corrective measures would be necessary to properly balance the pool water. However, if your school does not have access to a swimming pool, you can still test regular tap water to determine the suitability of the water source for use in a common commercial swimming pool. In this situation, you would still need to analyze what treatment options would be necessary to optimize or balance the water before it could be used. Either way, the students will still be able to conduct a wide range of experiments to test a water sample, analyze the results. However, I should warn you, although most people think that testing pool water is a simple task, it's actually quite demanding, as you'll see in just a moment. As I mentioned before, test strips are not particularly useful as they lack precision. Therefore, the results that you get from test strips can easily be skewed. That is why commercially operated pools are required to conduct professional water tests on a regular basis. In this example, I'm showing a lab setup from BioGuard, which is a company that I have a lot of experience working with. However, other companies such as Lamont, Taylor Technologies, and Fisher Sci also provide commercial testing solutions for commercial pools. Now, as you can see by this lab setup, testing pool water to meet health and safety regulations is no joke. It's a serious task, so let me take a moment to explain the different tests that must be conducted by the lab technician. The first test is to determine the amount of dissolved solids, or TDS. Using a TDS meter, the conductivity of dissolved ions is tested. This is done by sending out a small electrical charge through the sample to measure the electrical conductivity in the solution in what's called Siemens. If you're unfamiliar with the term Siemens, it's the SI unit of conductance, and it's equal to 1 reciprocal ohm. Now, ideally, the lower the TDS level, the better. However, it's also important to note that not all pools use chlorine as a sanitizing agent. Some pools, particularly in Australia, use salt instead, and this will affect the TDS level of the water. Regardless of the sanitizing agent being used, testing the TDS level of the pool is an important first step in determining the overall quality of the water sample. The next test is for total chlorine and typically uses a 10 milliliter water sample. A reagent which changes colors depending on the concentration of chlorine is added to the water sample. That sample is then held against a white backlight and is compared against an accurate color chart. With BioGuard, the reagent comes in pre-measured tablets, which is then dissolved in the sample. This ensures that the addition of the reagent is perfectly measured every time. However, other companies such as Taylor use a liquid reagent, which is a little bit easier to use in high-volume situations. That being said, the droplet size can vary slightly depending on how hard you squeeze the reagent bottle. The next test is for free chlorine. Now, both the total chlorine and free chlorine tests should be done simultaneously so that the values can be compared. Ideally, these two values should match. However, there are numerous situations which can cause a discrepancy. These scenarios would indicate a serious problem with the pool water that needs to be addressed. Furthermore, if either of the chlorine levels exceeds 5 parts per million, the results of the other tests can be skewed. While professional tests using reagents and neutralizers can accommodate for this, a generic test strip cannot deal with this issue. The next test that needs to be done is pH. Now, if the chlorine value exceeds 5 parts per million, you can get a phenomenon called bromophytal blue. In this case, the pH reagent turns a dark purple, which would indicate a very high pH. However, in these situations, the pH is usually very low. Therefore, it's easy to misinterpret the results of the test and recommend the wrong treatment to address the problem. That said, if you know that the chlorine level is high before conducting your pH test, you can act accordingly. All you need to do is add chlorine neutralizer to the water sample before adding phenol red to test the pH level of the water sample. The next test is for manganese, which can cause damage to the pool's surface. After that, additional metals such as copper are then tested for. Now, copper can enter the pool water in a few different ways. If the pH is low, the acidity of the water can start corroding the pool equipment. However, this is becoming less common as most companies are now avoiding using metals in places that are exposed to water. Alternatively, copper gets added by people all the time, particularly when a pool is being neglected by its owner. In the event of a large algae bloom, many pool owners turn to copper sulfite, which can be purchased at many department stores. While the addition of copper sulfite is an effective method to eliminate the algae, it does create a series of serious problems that need to be addressed before the pool can be used again. And finally, the last metal that's tested for is iron. Since this reagent smells like rotten eggs, you're likely going to have students complain about it if you do this test in a poorly ventilated classroom. The next test in the series uses a chemical titration to determine the total alkalinity of the water sample. For this test, you'll measure 100 milliliters of water using a graduated cylinder, which will then be poured into a large beaker, which has a volume no less than 250 milliliters. Then, using a magnetic stir plate, you can slowly stir the water sample during the titration. Start with a slow flow of reagent at first until you start seeing a color change. Then, reduce the titration to a steady drip. Monitor the color of the sample after every drip, and at the moment the sample changes from a bright yellow-orange to a dark orange color, stop the titration. Then, take a measurement from the burette to see how much reagent was used. And finally, the final test is to determine the calcium hardness of the water. This test also uses a chemical titration, but the reagent will go from a vibrant pink to a dark purple during this test. Now, as there's no way to practically remove calcium from the water, the only way to address calcium hardness is by draining some of the existing water and adding soft water to replace it. Typically, the calcium level of the pool will be balanced when the water is first added and is not adjusted unless a large amount of fresh water has just been added to the pool for some reason. However, the use of calcium hypochlorite can also slowly affect the calcium hardness of the pool over time. This low-cost granular chlorine shock has a relatively low chlorine content per molecule, slow to dissolve, causes the water to go cloudy, and is also molecularly unstable. And this can lead to the compound spontaneously combusting during storage. However, due to its relative low cost, many commercial operators like to use this product in their regular maintenance routines. And that brings me to the idea of safety and why it's important.
Well, it's almost summertime officially next week, and you know the heat has a lot of families heading to backyard swimming pools. But tonight, we have a warning if you're treating that pool yourself.
This comes from a family in Greenwood that's still cleaning up today after some pool chemicals reacted in their home earlier this week. It caused a large explosion and sent the couple to the hospital for treatment. Naomi Pescovitz explains what happens and what they say you should know.
The couple who lives here consider themselves experienced pool owners, and they treat their own pool all the time, which is precisely why they want to share their story with others. They never thought these two bags could do this much damage.
This one I had poured in first and poured this one on top of it, and when it was just the powder, there was no problem. And then I added water, and when I added the water, it just exploded. I mean, it really did. It was so fast, within seconds.
Two different brands of swimming pool shock treatment turned into a cloud of toxins in the kitchen.
I dropped the pitcher into the sink, and it started to shoot. Like, it sounded like mortar. It just was a pow, pow, pow.
The sink dropped. Pictures flew off the walls. Days later, the chemical is still splattered everywhere. The couple didn't want to share their names, but they do want other pool owners to know what happened.
It was shock. We thought it was all kind of the same thing, and so you just kind of add it together and you throw it in your pool. It's water, so you add water. You don't think there's going to be any kind of a reaction, and we added water and there was a major reaction.
They could be upwards in the range of $20,000 to $30,000 of damage in the kitchen.
The chief of the Bargersville Fire Department says this was simply a mistake, but one that could happen in any home.
Our homes are filled with dangerous chemicals, whether you have a pool, cleaning supplies, any other thing, and it's, you know, you just got to be careful mixing those and even how you store them.
Despite some respiratory problems immediately after the explosion, both husband and wife are fine, though the loud blast burst the woman's eardrum and left burns behind her ear. She was wearing this rain jacket, which shows how much worse it could have been.
Really, that's what took the brunt of it, was that coat. That's, to me, that's kind of the epitome of what could have been my face.
Now the family is left with all this cleanup, dealing with insurance, even a hazmat crew coming in, but thankfully it's all material and everyone's okay. And
now, to avoid dangerous chemical reactions like the one we just saw in the short video, you should never mix random chemicals together. And you should always add chemicals to water, and never water to chemicals. Now, I don't expect your students would ever be adding chemicals to the school swimming pool. However, this one safety tip is incredibly relevant to any experiment that you'll do in the lab. And finally, while the dangers of chemicals such as calcium hypochlorite cannot be understated, there's another chemical that's commonly used in many pools that's even more dangerous. This chemical is sodium hypochlorite, which is more commonly known as liquid chlorine. Furthermore, this chemical is often used in conjunction with hydrochloric acid in many commercial pool setups. However, these two chemicals can result in violent explosions and will produce chlorine gas if accidentally mixed. Now, for reference, this is the same chemical reaction that was used to create chlorine gas during the Holocaust. Now, cautionary tales aside, the next thing that students would need to do is to analyze the results and then make the necessary calculations. And this is a great time for students to apply three-dimensional geometry or the use of any of these formulas to quickly estimate the volume of a pool. Alternatively, depending on your student's grade level, students could also use the summation formula, like the one that I've shown here from this textbook example. Then, with the volume of the pool determined, students would then be able to review the instructions for each chemical and determine the correct amount of each chemical that will be needed to correct for any imbalances in the pool water. Finally, one of my favorite inventions in the pool industry is the saltwater generator. First invented in 1972 by Cascade Pools in New Zealand, these little devices can turn standard table salt into a usable form of chlorine and then back again, making this a sustainable and environmentally friendly solution to pool chemistry. Now, while this method of pool sanitation is not common in North America, countries like Australia, which are relatively isolated from their trading partners, tend to use saltwater generators almost exclusively. Environmental and economic factors aside, the required level of salt needed for this, the effective generation of chlorine is equal to about 3,000 parts per million, which makes the chemical composition of the pool water almost undistinguishable from saline. As a result, the natural chemistry of the pool water is ideally matched to our human physiology. Now, you might think that the chemical reaction that happens in a saltwater pool is relatively straightforward. Salt is converted into chlorine and then back again. Think again. The actual process that's happening is quite complex, so let's break down what's happening. First, salt is dissolved in water, which causes the molecules to ionize. Then, using a process of electrolysis, the charges of the sodium and chlorine ions are stripped away. This will result in the formation of a metallic sodium and chlorine gas inside the generation chamber, and this process is accomplished using a 12-volt electric charge and a series of polarized platinum blades. Now, the use of platinum makes these generators incredibly expensive to buy, but it's the only metal that can withstand the corrosive nature of the chemical reaction. Then, the metallic sodium will instantly react with water to create hydroxide and hydrogen gas. And the second reaction that will happen will be the hydrolysis of the aqueous chlorine gas, which will result in the formation of hypochlorous acid. This will immediately be followed by the dissociation of the hypochloric acid, which will result in the formation of hypochlorite and hydrogen gas. All this happens in a mere instance, and this is what the chemical reaction for all these reactions would look like. Now, you're probably saying, wow, that's complex. But this is only the first half of what's happening. The reaction will then result in the formation of sodium hypochlorite, which will eventually break down to create salt and a small amount of hydrogen off-gassing, and a small buildup of hydroxide over time. As such, the entire reaction will also cause the pH of the pool to rise slowly. However, the natural tendency of a pool is for the pH to drop over time as a result of sweat and rainwater, which are both acidic. Therefore, the natural byproduct of this chemical reaction actually helps to offset the undesirable trends in the pool's natural chemistry. However, If natural causes do not keep the pH in check, the use of hydrochloric acid can be used to help regulate the pH. As you can see, something that seems simple enough actually requires a quite in-depth study of molecular chemistry. And that's what STEM is all about, learning rigorous academic concepts while applying science, technology, engineering, and mathematics in a real-world context. And that brings me to my next example, photography. Now, while most people think that photography is just a simplistic art form, history teaches us something completely different. So I want to start by sharing this example with you. It's one of the most unique requests that I ever received while operating my company. It was to photograph an entire museum collection. However, this glass was unique as the artist was known for using uranium. Yes, you heard me right. Some of these works are enriched with uranium. Now, you cannot see the effects of the uranium under normal light. However, if we apply high energy particles that are outside the visible light spectrum, the uranium will absorb the energy and irradiate it as visible light, much like the energy transfer process that happens with the Earth, which converts ultraviolet rays from the sun to infrared radiation. So this is what these artworks look like in the dark. Spectacular, if you ask me. But one thing that you'll notice is that we were unable to tell which one of these examples had uranium based on what we could see with the human eye. Therefore, the only way I could go about doing this project for the museum was to understand chemistry, physics, and the art of photography. So now that I have your interest, let's look at some chemical advancements that have been made as a result of photography over the years, because many famous photographers throughout history were in fact scientists. The ambrotype was one of the first types of commercial photographs. With this method, photographers would take a simple glass plate and coat it with a thin layer of iodized collodion, which was then dipped in a solution of silver nitrate. The plate would then be exposed to light inside the camera while it was still wet, and this was incredibly difficult to do. Moreover, the exposure times varied from 5 seconds to more than a minute, and this made photographing objects even more difficult. The glass plate would then be developed and fixed through a series of chemical processes. The result of this created a negative image, which would then be viewed by reflecting light against a black background, which would make the image appear as if it was positive. This was because the clear areas would appear black and the exposed areas would appear relatively light. Moving on to Louis Daguerre. The invention of the daguerreotype advanced photography, as this process had significantly better quality, was more durable than the glass ambrotype, and was easier to work with. Now, the daguerreotype would form an image on a polished silver surface. These highly polished silver plates were then made light-sensitive using iodine fumes, which would produce a light-sensitive silver iodine coating. This light-sensitive silver plate would then be exposed to light inside the camera. The latent image would then be developed in a purpose-made developing box using mercury vapors. Then, after development, any unexposed silver halide would be removed using a metallic solution of sodium thiosulfite. While the ambrotype was difficult to handle and incredibly fragile, and the daguerreotype being incredibly toxic, it goes without saying that these methods would be unsuitable for students to learn in school. However, photographic methods that use silver iodine can provide students with excellent cross-curricular learning opportunities. Even without fancy camera equipment, students can explore the scientific and artistic aspects of black and white photography using a pinhole camera. In this situation, photographic paper is placed in a box in complete darkness. A pinhole is then made on the opposite side of the box, which is then covered with tape. The tape is carefully removed to start the exposure and is then replaced to stop the exposure. To print the print can then be developed in a darkroom or even a bathroom sink, providing that you do not expose the paper to any white light. Now, while Kodak's bankruptcy in 2012 was a big blow to the black and white community, it did not stop professional photographers and enthusiasts. And this was because the legendary D76 solution can be made at home or at schools using some common household compounds. First, start by adding 750 milliliters of distilled water at a temperature of 52 degrees Celsius. Then add 2.5 grams of methyl and 5 grams of hydroquine. Add 100 grams of sodium sulfite and anhydrous. And the last chemical that needs to be added is 2 grams of borax granular. The final step is to add an additional 250 milliliters of cold water to bring the solution down to 20 degrees Celsius, which is the optimal temperature for developing film. Now, if all that sounds too complicated, don't worry. D76 is still made under the Kodak name by a third party, which has kept this product alive to this day. Now, after the developing stage has been completed, the chemical reaction needs to be neutralized by a process known as stop bath, fixed, and then washed. So the stop bath neutralizes the alkaline developer, thus halting the development process. Now, stop bath is typically comprised of a diluted solution of acetic acid. Therefore, you can actually use household vinegar if you want. However, a solution of potassium or sodium metabisulfate can also be used as well. Next is the fixer solution, which removes any unexposed silver. The fixer solution contains sodium thiosulfate, sodium sulfite, and sodium bisulfite. And finally, the wash. Now, there's nothing special about this, but some photographers do like to use a product that's known as PhotoFlow to reduce the required wash time so that they can conserve water. As I mentioned before, you can still buy black and white chemicals. Not only that, but there's also been a resurgence of many new products coming to the market in recent years. This is because there's still some advanced photographic processes that can only be done using chemical-based photographic solutions, and this makes film the go-to solution for several specialty niches. For instance, 2 specialized products that I've used in the past are Ilford nuclear emulsion and infrared films. And I'm also particularly fond of Fujiacro's film in combination with Ilford fine-grained developer for ultra-high resolution imaging. Now, if you're interested in some of the scientific applications of these specialty products, infrared film is great for astronomy and vegetation studies, but it can also be used for military reconnaissance. On the other hand, nuclear emulsion films are great for investigating charged particles and can also be used to find structural faults in things like bridges and airplanes due to material fatigue during a safety audit. So as you can see, there's a lot of science in photography, and I haven't even got into principles such as pushing and pulling film, reciprocity, the Scheinflug principle, or any of these other mathematical theorems. And these are all things that students need to learn when studying advanced photographic concepts at the university level. And finally, we'll explore chemical processes to recover precious metals and how we can adapt these methods to make them more appropriate for high school students. Furthermore, the idea of precious metal recovery also ties in well with the humanities as we explore the social, economic, and environmental aspects of our decisions. And this is something that the World Economic Forum has called for with reforms to STEM education. Now, regrettably, most e-waste is not recycled. But as you'll see in a moment, the recycling process is not overly environmentally friendly either. So by exploring precious metal recovery methods, we have an opportunity to explore the philosophical and ethical issues that are related to the consequences of our actions or inactions. However, one company that could change the way that we look at e-waste is Mint Innovation from New Zealand. And this is the same country that invented the saltwater generator as an environmentally sustainable solution to pool water sanitation. Now, Mint Innovation has developed a revolutionary new method for recovering precious metals such as copper, tin, gold, and palladium using microbes. While this process is not something that we can explore in a high school setting, it's a great case study to share with the students either before or after learning how traditional chemical processes work. Now, if you want to do an e-waste lab, the first thing that you'll need to do is to collect scraps that contain precious metals. And circuit boards from older computers do tend to be better for this kind of experiment. But what type of components have the highest concentrations of gold? Well, the best sources of gold can be found in the female connector pins that are plated with gold. The north and south bridges contain microscale gold wires. PCI and memory card slots have gold-plated pins. Integrated circuits contain gold wires. Any visible gold-plated pins are worth mentioning. And while it won't be relevant to this experiment, monolithic capacitors are great sources of other types of precious metals, such as silver and palladium. Please note that you'll also need about 6 kilograms of scrap to collect enough gold for this type of lab experiment. While mimicking commercial e-waste recovery methods would be ideal, The physical limitations of the classroom learning environment are somewhat prohibitive due to the lack of time, space, and resources. However, we can draw inspiration from these commercial practices and then simplify them. So let's start by analyzing some of the differences. First, official recycling processes require a large number of exotic chemical compounds. These compounds allow the chemical process to completely dissolve the entire structure of the material to be recycled. As a result, the superiority of this process will allow for the precious metals to be all of the precious metals to be recovered. For instance, once the entire circuit board has been dissolved in acid, different chemical compounds can be used to precipitate each metal out of the solution in a specific order, based on its electron affinity and reactivity level of the precious metal to be recovered. These metals will include copper, lead, iron, and the more precious metals such as silver, gold, and palladium. Once each metal has been precipitated out of the solution, it will then need to be refined before smelting. While this process is too complex to explore in school, a simplified process that only recovers the exposed gold can provide students with an authentic learning experience. And this type of e-waste lab also works well in schools that have a breaker space, as in the primary division, as these activities tend to result in an accumulation of e-waste that can then be used by students in the senior school. Now, to get started with an e-waste lab, you'll need the chemicals and equipment listed on this slide. You'll need the following chemical compounds: hydrochloric acid, hydrogen peroxide, nitric acid, sodium metabisulfate, stannous chloride, and sulfuric acid. Furthermore, you'll also need a number of standardized lab items. And finally, there are a few things that you'll want to use which will make the recovery process even easier. These items include a small DC air pump which can be used to agitate the solution, vacuum filtration to improve the filtration process, and a magnetic stir plate to make it easier to mix the various solutions that you'll use during this lab. Now, this process is only capable of recovering the exposed gold that's found in the connecting fingers of a circuit board. Therefore, it's best to use a paper guillotine or tin snips to cut the fingers off and send the remaining circuit board off to a commercial recycling facility. Then, place the scraps in a large 3-liter glass beaker before adding 1 liter of hydrochloric acid. The clear hydrochloric acid will start turning green as it reacts with the various metals from the circuit board. Now, the gold connectors on a printed circuit board are typically overlaid on top of other conductive metals. Our objective here is to allow the hydrochloric acid to start dissolving the underlying materials. After about 10 minutes, slowly add about 100 milliliters of hydrogen peroxide to the solution. This will cause a chemical reaction that will produce off-gassing, heat, but more importantly, it will produce a large number of bubbles which will agitate the solution. This turbulence within the solution will help dislodge the gold from the surface of the circuit board. It's also recommended that you cover the beaker to contain the fumes and avoid any unnecessary dilution of the acid. Then, let the reaction continue for a minimum of 12 hours. Therefore, it would be practical to let the reaction go overnight so that the students can come back to the experiment the following day. At this point, the solution will have changed from a green to a dark black color. You'll then need to add another 100 milliliters of hydrogen peroxide. This further dilutes the solution while also rejuvenating the chemical reaction. Then, repeat this process twice over a 72-hour period. Due to the time that it takes for this process, you'll likely want to split up your lessons. Have the students spend a few minutes addressing the practical requirements of the lab, and then the remainder of the class can address theory. This could include updating their lab books with observations, procedural notes, and covering the theoretical aspects of the lab itself. After 72 hours, the solution will be ready for the next step. At this stage, you can pour out the solution into a clean beaker. Keep the solution as it will need to be filtered to remove any gold before disposal. Next, using thick rubber gloves and a water spray bottle, you can wash the scraps. Make sure that you inspect all the scrap metals to see if there's any gold remaining on the circuit before discarding it. With the scrap thoroughly washed, you're now ready to filter the blackened acid to catch any fine particles in the solution. Pour the solution into a funnel with filter paper in it, or better yet, use a vacuum filtration unit like the one shown on this slide. For optimal results, be sure to pre-wet the filter before using it. Once the entire solution has been filtered, you should be left with gold particulate in the original beaker and some finer gold particulates that have been caught by the filter paper. You can now dispose of the initial acid solution. Please note that there will be dissolved metals such as iron, lead, copper, and other metals that could be recovered using more advanced methods. However, these methods are much more complex. Moreover, as gold is the most valuable metal and time is limited, it's practical only to focus on extracting gold in an educational setting. Next, carefully remove the filter paper and place it in a clean beaker, as it will be full of gold powder. Then let the filter dry. At this point, you'll have a beaker that has gold sludge in the bottom of it and another beaker with filter paper that's full of small gold particulates. However, this gold will still contain lots of contaminants. Next, we'll remove contaminants from the gold residue. Using a 1 liter beaker and add all the gold residue that's been collected and add 200 milliliters of hydrochloric acid. Then add small amounts of nitric acid using a dropper, pipette, or burette so that you do not end up with an excess amount of nitric acid in the solution. At this point, the gold will start dissolving and you'll see red nitrogen dioxide fumes forming. Make sure that you avoid breathing in these fumes. Once all the gold has been dissolved, filter the solution again to remove any contaminants such as fiberglass and plastic from the solution. Be sure to thoroughly rinse your beaker, funnel, and filter paper with water until the solution runs clear, as the residue will contain gold. The next thing you'll want to do is to create a saturated solution of sodium metabisulfate. Using a magnetic stir plate, slowly add sodium metabisulfate granules to water until the solution can no longer accept any more. This is when the granulars no longer dissolve and start accumulating at the bottom of the beaker. Then add your filtered gold solution to a large 1 liter beaker. At this stage, you can now add sodium metabisulfite to the gold-bearing solution. The sodium metabisulfate will react with the hydrochloric acid in the solution, which will create sulfur dioxide. The gold ions will be attracted to the sulfur, which will cause them to fuse together and drop out of solution as a metal particulate. Allow the heavy gold particles to settle at the bottom of the container, then wait a minimum of 4 hours or even overnight before proceeding to the next step. Next, conduct a stannous chloride test to see if there's any gold left in the solution. The remaining solution should be translucent brownish color at this point. Carefully pour out the waste solution into a waste beaker without disturbing the gold particulate at the bottom of the beaker. Check the waste with stannous chloride one more time to see if any gold is left in it before disposal. Then rinse the gold sludge with warm water and allow the gold powder to settle. Once all the gold has settled, carefully discard the wash water. You'll be left with a gold mud at the bottom of the beaker. At this stage, you could dry the gold powder, or you could process it further. My recommendation is to process it even further. To continue filtering out impurities in the gold, you'll need another 400 milliliters of hydrochloric acid. Apply medium heat and stirring. As the hydrochloric acid boils, it will react with any remaining metals that are in the powder, and the solution will start getting darker. This will most likely be a result of iron being present in the solution. Let the solution settle and then perform another stannous chloride test. If the acid solution has dissolved any gold, you'll need to add small amounts of sodium metabisulfite solution to precipitate the gold out of the solution. However, it's important to add it slowly, as you do not want to precipitate other metals out of the solution in the process. Therefore, you'll need to keep conducting stannous chloride tests to help you identify when you should stop adding sodium metabisulfite to the solution. Then, once you're done, pour the wash water and rinse the gold powder with hot water. Then let the gold settle and pour up the wash water the same as before. At this point, you could melt down the gold, or you can purify it one more time by conducting another round of hydrochloric acid followed by medium heat and stirring, followed by small amounts of nitric acid. After about 1 hour, you'll have an orange solution. Allow the solution to cool before adding sulfuric acid, which will react with any dissolved lead, which will precipitate out as a fine powder. Vacuum filter the solution and be sure to rinse your beaker, funnel, and filter paper with water, as they will contain gold. The lead precipitate will be caught by the filter. Then add sodium metabisulfite to precipitate the gold out of the solution. Conduct another stannous chloride test to ensure that there's no gold left before discarding the waste solution. Then rinse the gold powder in hot water again, and once the gold has settled off, pour off the rinse water. Then let the gold dry and pour it into a crucible. Use a torch to melt the gold and pour the molten gold into a small jeweler's mold. Upon completion, you'll now have a small nugget of gold that will be approximately 20 karat gold. And that brings us to the end of this presentation. I hope that you found this in-service program informative and that you've been able to take away several ideas that you can use to design authentic learning opportunities for your students. while also learning how to use chemistry to solve a variety of real-world problems. And with that said, I'd like to thank you for giving your precious time to attend this presentation of applied chemistry in STEM education.